So morning, I must say I picked a confusing title here. We use the consensus board a lot in this industry. Some might even say it's abused. And really, I want to talk about design consensus, which is different from blockchain consensus we know every day, because machines talk to each other to reach blockchain consensus. But here I want to talk about human side, where we design things, we also need to reach consensus. And I also want to do this talk a little slightly different. As you can see, I have a few pages here. I'll read exactly what I have on here. This way I can get my words right. And a minor suggestion here in next CKCon, maybe we can have a prompter so everyone will have an easier job. So back in the early days, we designed CKB-VM and together with the CKB script execution model. So CKB-VM strictly followed RISC-V spec, which is more the objective part. But the execution model is really the subjective part, where we bake a lot of our own likes and preferences into the thing. Mostly it's my personal own likes and preferences. Lately, I found that some CKB features are really not used in the way they are designed for. I'm not saying that anyone used it wrong. I'm just saying this could be a really good opportunity to tell the differences. And hopefully we can read some discussion. And a big warning here, this talk is gonna get real technical, so I hope all of you had your coffee. And really the first thing I want to discuss is hash type field in the script data structure. As you might already know, each CKB cell has a mandatory log script. Some of them has an optional type script. A CKB transaction, when it's committed on chain, both the log script and the type script from the input cell will be executed as well, and also the type script from each output cell will also be executed. All of those scripts have to be executed and finished with a success return code, and only in this way a transaction can be committed on chain. And both log script and type script have exactly three fields: code hash, hash type, and args. Args is now the focus today. I want to focus on code hash and hash type field here. The script data structure do not actually contain the CKB code itself. It merely acts as a pointer to the real code which is embedded in the depth cells. A code hash always contains a hash of something. Here I use something that's short and we can know that, but really this 0xEEE, 0xBBB really refers to a cryptographic hash. The hash type, on the other hand, tells us what the hash in the code hash part really is. If the hash type contains the value of the hash type is type, it tells us the code hash for that structure really contains the hash of another type script, which is from the depth cell. And if the hash type is the data 1, data 2, or any of the data variants, it tells us the code hash from the same type script refers to the actual data hash from another hash of the cell data from another cell depth. I want to know that there are actually two type scripts in some cases. The first type script on the left is the type script you want to execute, and the second type script comes from each depth cell, which is like a marker for that depth cell. So make sure you can distinguish between them too. So I pressed the wrong button. So this mechanism looks simple from the outside, but it enables us to build a cell for which we can upgrade this code. And as shown here, we have a type script A. You can locate a cell B on chain using the type script A's code hash and the hash type combination. A later time, cell B can be upgraded into cell C. But the same type script A can continue to locate a cell C because the code hash and the hash type matches. And really, the interesting thing here is the type script in this cell B and cell C can guarantee that on chain, there's only one cell can have this type script. There's no ambiguity here. Type script can uniquely locate only one cell on chain. And this whole part is really an optional mechanism. You can use it, but you don't have to use it. And really throughout the years, it seemed to us that this feature is not used as it should be. For starters, some libraries, for example, CKB SDD, which is maintained by Cryptape ourselves, have APIs that only require code hash, but just ignore the hash type part and assume that a particular value is using the hash type part. So really here comes my first suggestion. Please, please, please never use code hash alone. When you want to identify a piece of code, always use the combination of code hash and hash type. And this way we can make sure there's no ambiguity everywhere. And the above is really a suggestion that is crystal clear and should only results because of miscommunication. The actual usage flow for type ID here right now is really not the way when I originally designed this thing. So I want to take this time to talk about it, and hopefully we can have some discussion afterwards. The really key part is that in each cell using the type ID as the type script, you are free to change the log script to anything when you upgrade the cell. It's not just just that you can upgrade the actual code in the cell data part. You can actually also update the log script here. So the original design or workflow here is that when a piece of code is first deployed, we are free. It might contain bugs. We may not know enough features have been developed. But as people start to use the code, they may want more features, or they discover bugs, or there are certain security leaks. We had something like this before. At this time, when you're using type ID as the type script for the cell, you can just upgrade this code. And the new code can contain bug fixes and new features, and you can do this for a few iterations. You might reach a point when either because you say that, okay, now we know enough about this code. We know it's mostly free of bugs. It has enough of our features. Or another reason could be that there's enough asset controlled by the log, but by the actual deployed code. It presents a security problem if the code is continued to be upgradable. At this time, you could just do a final upgrade and change the log script to something that's now changeable. This way, even though you still reference the code using the type ID mechanism, there's no way anyone can change the log, change the actual code. The code will be freeze forever. So this is really the original design way to use TypeScript. The other thing I want to point out here is that there are actually two differences. A script developer, someone who's writing RISC-V code, can deploy the script in any way they want. They can deploy the code using type ID, or they can choose not to deploy the code in type ID. But the app developer who is using the code can also has the option to use the type ID mechanism or not. Here's an example of this. We have a single UDT cell which is deployed on chain, and before we have version 1, it's deployed with type ID enabled. But someone who's using this UDT cell can either issue their token using the type ID, like the UDTA here, or they can choose to use just the exact code without the type ID mechanism, like UDTB here. So later, when the UDT code is upgraded from version 1 to version B, UDTA will pick up the new code directly. But UDTB, this group of people controlling UDTB will maybe they follow the code's law principle strictly. They want to still use the version 8. They have the option here. They can just do that. Some might say that, the code is upgraded from version 1 to version 2, but so the live from version 1 is not the left cell. We cannot reference it anymore. But if you track the CKB history, the actual code is still locatable. Everything on chain is public, and even including all the history. So you can just simply deploy the new cell here containing the version 1 of the code, and UDTB will continue to function here. And some might say that we have to use CK BIOS to deploy the cell. This answer is yes. And the solution here is that you can deploy this, redeploy the version 1 cell and control your UDTB to work in however way you want. Then you can just discard this cell, reclaiming the CKB bags. Or another solution is like, there could be a lending market providing people with new cells like the version 1 deployed here, and people continue to use the cell with the same thing. This is no concerns about this part. So those are really the original idea when I introduced CKB. So some of it got lost in the history. I just want to reintroduce them. Hopefully we can have some discussion afterwards. The next thing is two syscalls, exec and spawn. And syscall is really a wide-used term from operating system. If we draw a little back from the literature, it grants a CPU access to external entities. For example, in modern operating systems, syscalls allows us to read a file on disk, execute a new program, or access the network. In CKB, however, CKB can help CKB VM to read the contents from the current CKB transaction or perform other duties. And really, exec and spawns are two examples of syscalls that perform certain opportunities. It allows one script to call another script on demand. Let's consider a real scenario, assuming we are building a new script here. Actually, I'm going to use code and script interchangeably because they really refer to the same thing here. The script verifies some structures or calculates some hash. Right now, for the moment, maybe we know and use SECP256K1, SHA-256, Black2B, and we know this thing can be embedded in the code, in the code when we deploy it. We can, however, there are new algorithms coming out every day. What if one day maybe we want to add AD25519 or Black3 to our solution? Of course, one choice is that you can upgrade the same cell to contain more code, but the problem is with more dependencies, you have a larger attention focus. And also, the binary size can get large, so one cell won't fit it. In other scenarios, some scripts may not be upgradable at all. Is there a better solution? So really, exec and spawn provide a different solution to this problem. They allow your main script to call a different piece of code, and the different piece of code provides more functionality. Take the above example, we can build a piece of code doing the ED256-25519 verification, or deploy a different cell that calculates hash in the Black2B algorithm. And our main script can just use exec or spawn syscall to call into those different scripts to perform the functionality. My colleague, I think my colleague is going to present a talk on spawn syscall right after me, so I won't go into more details. I just want to point to the differences between exec and spawn here, because when you call another script using exec, the control, the execution control is completely transferred to the new script. For example, when our main script calls into, for example, ED25519 script, our main script gets lost. The return code of that callee script will become the final return code for the current script. Spawn, on the other hand, actually created two VM instances where each run its own code and they can talk to each other to exchange information. When the callee script called by spawn terminates, the main script can obtain its return code and the main script continue to run. In fact, spawn is the combination of two more primitives, fork and then exit. Assuming in Linux we type ls in the bash shell, the bash process actually first cloned itself using the fork syscall. Then the cloned bash access executes exit syscall, replacing itself with the ls program. The ls program continues to run and finally decides to return, and it will just terminate, but our main bash process continues to function. And it really is just like an optimization that people combine fork and exit into a single syscall called spawn, because you can skip many parts in the middle. I personally designed exit when we do the first hard fork in 2022. And when I designed the exit syscall, I actually have fork in mind. But the problem here is that we don't have really, back then we didn't have a really clear picture how many cycles we should charge for the fork syscall. We don't know on-chain usage very much. It was a really early time where only a few scripts have been deployed on-chain. So there's no way we can know a proper cycle charge for fork syscall because fork does not only incur CPU time, it also consumes more memory because if you're doing fork, you have to create more VM instances. The second problem is really a more controversial one. I do believe that a majority of our CKB code we deploy every day could be re-architected or reorganized into a different way where we first do some transaction level verification. And finally, we leave either a signature verification work or hash calculation work to a different script. If you think about it, if every script could be re-architected this way, this workflow fits very nice into syscall. But and this way, if we all just use this exit by re-architecting our script, the resource usage of CKB could stay constant because we know each single script will have only one VM instances. But really, unfortunately, this idea doesn't get enough attention. In hindsight, maybe I should do more introduction and maybe I should do more examples, but the reality is actually never gets the attention it deserves. So right now in 2024, we have Spawn in the work and this problem will go away, but yeah, it's like a problem. I hope we have done better. We should have done better. Related to exec and Spawn syscall, back at the time, I also designed OmniLog. It was designed to capture enough features so it could be a general log script. For example, it could capture things like anyone campaign mode. Anyone campaign mode was a thing back then, and right now is pretty much abandoned. And also, it could capture time log mode where you can set a log on when a single cell could be a log. On the other hand, it provides enough signature or verification algorithm so it could capture the workflow, the verification workflow from CKB, from Ethereum, and from Bitcoin. If we look at it today, OmniLog was an early attempt, but it presents two unique, interesting points, and here's the first one. It demonstrates the needs of a general, widely used log script. We should have such a log script to replace the SecP256K1 log shipped in the Genesis block. The one in the Genesis block really is the fail-safe solution, or I'll typically call it a fallback log. When all other logs cannot be used due to certain problem, only when then we should use the log from the Genesis script. But for some reason, people start to use the log from the Genesis log and call it the default log, which raises a lot of different problems. Looking back, if we want to do it a second time, maybe I think we should, like in 2019 when CKB mainnet is first launched, we should probably deploy a new log right away and have people start using that log. And this way we can just like avoid this default log versus fallback log debate from there. And really the default log, the fallback log from Genesis block should stay as a last resort we have. But we never get a second chance. And really, despite the fact that OmniLog ships some signature verification algorithm, it contains solution for several signature verification workflow. Then by no means to be an exhaustive list. OmniLog in the first version can already call other scripts where the exit syscall for signature verification task. In this example, OmniLog calls into ED25519 script to do the signature verification. This aligns with the previously mentioned exit workflow here, where a script does its initial verification and then calls into another script for more tasks. But the reality is we keep adding more signature verification algorithms right into OmniLog and keep upgrading OmniLog. I wasn't sure how we got there, but maybe a miscommunication from my side lead to these results. And I hope I have a little time because finally I want to talk about precompiles. Actually, the lack of precompiles, which is an important thing for us. I don't have enough time, so I'll just jump to the last slide. I hope you all know what precompile is because I really want to say this. I believe the lack of precompiles is important because the lack of precompile really means that we are a permissionless public blockchain. Everyone is free to deploy a new implementation for signature verification algorithm or implementation for other algorithm into our code. You don't need a permission from the foundation, which is unlike almost any other blockchains out there. You can just deploy the codes as you see fit. I believe this is really important value for us right now. As long as I'm working on neural CKB, I will fight so CKB VM is free from any precompiles, because I personally believe the value of the lack of precompiles. Only the lack of precompiles makes the CKB a true permissionless public blockchain. Thank you. Hope you can have an awesome CKCon conference.